One qubit, which is, as I said, kind of a combination of zeros and ones. We have these complex numbers. We throw in square root of -1, is two-dimensional. And so you basically have two numbers that are associated with this. Now, compare that to a bit, which is simply 0 or 1. None of this that's in fact, zero-dimensional. That's just 2 points. That's zero-dimensional. All right, so one qubit, one piece of quantum information, two-dimensional. And there are infinite number of possible values, not just 0 or 1, infinite number. We control them, what they are. They're not arbitrary, but they're still an infinite number. I add another qubit. That goes to 4 dimensions. And you say, I can do math. I can say that 2 plus 2 is 4. It turns out, yeah, that's true, but it's really 2 times 2, the way the math works. Because when I add a third qubit, it exists in an 8-dimensional space. 2 times 2 times 2. And I add another qubit, it's a 16-dimensional space. I have 10 qubits, it's 2 to the 10th power, or 1,024. So you have to represent this in one standard ways of doing this by 1,024 numbers. It quickly gets big of how to do this, but this is the good exponential growth. It's 2 to some power, to some exponent. So you better become awfully comfortable with this slightly abstract way of dealing with multidimensional spaces. But it is this power that gives quantum computing the potential of dealing with very large problems.
Hello and welcome to Urgent Futures, the show that finds signal in the noise. I'm your host, Jesse Damiani. I'm a writer, curator, and professor who's on a continual quest to learn about reality and how it's evolving. Each week, I sit down with leading thinkers whose research, concepts, and questions clarify the chaos, from culture to the cosmos. My guest this week is Dr. Bob Sutor. Dr. Bob Sutor has been a technical leader and executive in the computer and deep tech industry for over 40 years. He is a theoretical mathematician by training with a Ph.D. from Princeton University and an undergraduate degree from Harvard College. During his career, Dr. Sutor has spoken to and briefed government legislators and policymakers around the world, such as his 2022 testimony before the United States Senate Committee on Commerce, Science, and Transportation on securing U.S. leadership in emerging compute technologies. He was a co-author of the 2024 Quantum Economy Blueprint from the World Economic Forum. Dr. Sutor is the CEO and founder of Sutor Group Intelligence and Advisory. He helps clients and advisors understand sophisticated technologies such as quantum computing and use them effectively to succeed in their organizations and industries. Bob is a member of the board of directors of New Quantum and an advisor to the Forma Prime venture capital firm. He is also an adjunct professor in the Department of Computer Science and Engineering at the University of Buffalo, New York, and spent over 2 decades at the IBM Thomas J. Watson Research Center. Dr. Sutor is the author of the best-selling 2019 quantum computing book, Dancing with Qubits. Over the years, you've probably heard many references to quantum computing. In geopolitics and tech matters, it's considered an area of extreme interest, and yet it remains a subject that many don't fully understand, even within the tech commentariat. That's why it felt important to host a conversation with somebody who could cut through the noise and explain the basics of the technology, including its promise and peril. Among Dr. Bob's many talents, he's a gifted communicator about this particular subject, and this conversation does not disappoint. If you've been looking for the opportunity to grasp the basics of quantum computing, this is a perfect starting point. So without further ado, please enjoy this illuminating conversation with Dr. Bob Sutor. I'm joined today by Dr. Bob Sutor. Bob, thank you for being on Urgent Futures.
My pleasure. Happy to be here.
Happy to have you. This is a subject that I've brought up peripherally in different episodes, but I've never done a proper episode on. So you are helping my listeners and viewers get much more acquainted with the idea of quantum computing. To that end, we'll need to do a little kind of elementary foundation setting that I know you do all the time, but I'm going to have to ask you again.
Yeah.
What is quantum computing and how does it differ from classical computing?
Okay. And to start, what we say is classical computing are the types of systems, such as in your phone, your laptop, the supercomputers, the servers on the web, and things like this. This architecture really goes back to about the 1940s. And when people talk about bits and bytes and things like this, it really boils down to we compute everything with zeros and ones. And when you get down to the semiconductor level, real circuits, it's all these logical switches, right? And they're doing ands and ors, and somehow you end up with addition and multiplication and can access memory and things like this. That's incredibly powerful. Obviously, if you look at anything we're doing regarding AI, these big data centers, the way we're talking right now, um, it's pretty great, and it's getting better. It's using more and more energy, right? I mean, as we get clever and clever, but it's worked really, really well. And in fact, if you were to go into a theoretical computer science class or book or something, you might read and say, anything you need to program, right? You can do it classically. And you say, well, that's great. And then you have this little asterisk and you say, though it may take millions of years to do this because the theoretical models, to say, well, let's assume infinite resources, right? And infinite amount of time and things like this. So it turns out that even though we can do a lot, there's a lot that's just not practical because even though we have these immense data centers and so forth, they're not big enough, or it would take so much time or so much energy, or would cost so much money. So people have for a long time started looking at other ways of doing computation. Maybe that's not zero one based. And quantum computing is based on an area called quantum mechanics of physics, started around 1900. So, for all of us thinking, oh, this quantum stuff, it's all new and everything. Yeah, 125 years new, right? But the reason is because people start to notice not just with like the properties of light and the normal sorts of things with physics. When you got very small, the rules didn't seem to apply anymore, and errors were introduced. Now, on the other hand, when things got really big, things didn't work either. And that's the part that people are much more familiar with relativity and Einstein and galaxies and E equals mc squared. So the well-known one is Einstein, probably thanks to himself because he was a great brand for all of that, right? Being the very big, and then quantum mechanics being usually the very small. Technically, it can do anything, but sort of. I'm obviously glossing over a few details here. And if we think about it that way, we can think of quantum mechanics as being the computational method for nature. So for every atom inside you, every electron, every photon of light, so everything in you, everything around you, and so forth, at its smallest level, is an app, right? We're all apps in that regard. And so people say, but what is the computing model? How do you program such apps, right? How does nature program such apps? And hence quantum computing. So you start with the very theoretical quantum mechanics. It's a very strange part of physics. Just if you really want to have your mind blown, and I know that's an old phrase, but it will happen. Look at quantum mechanics, and the things you thought were normal don't work. Right? However, maybe that's the normal, right? Maybe this other stuff we're doing is just like kind of a big hack, um, right? In the way nature works. So therefore, people have been exploring quantum computing to try to solve these problems that are just not practical for classical computing. It's relatively early days on doing this. The systems we have are nowhere nearly big enough to solve these massive problems, and it's very complex, right? And I want to distinguish complex from complicated, because complicated says, oh, this is just so complicated I can't get it straight. Complex is just there's so many things to consider. You have to um, harness these things, what we call qubits, from quantum mechanics that exhibit the quantum behavior. We have to control them. Oh no, errors are being introduced because you and I are quantum mechanical, as are everything we're doing, and they really want to mess up your math, let me tell you. Right? You're trying to do this thing in quantum computing, but the environment around tries to mess it up. So people are learning a lot. They're experimenting with about 10 different ways of doing quantum computing. Maybe 5 are primary, 4 or 5 are primary. But that's what it really comes down to. It's saying, how does nature compute? It's the most powerful computer in the universe. If we are the apps, let's steal that method and apply it to some of our hard problems. So problems in chemistry, in creating new materials. Eventually, and here we're going to need big systems, protein folding, new antivirals, and things like this. The forever promised personalized medicine. I mean, it's almost as long as I've been in the industry, people have been promising personalized medicine. So every new thing that comes along, right? Um, so those things kind of make sense because it's the chemistry, it's physical, it's quantum, and things like this. But if you look at the math and you look at some of the applications, yeah, okay, maybe eventually we can do some AI things with this. Maybe some types of optimizations, things where you start with a relatively small amount of data and then you try to start solving the problem, and it gets bigger and bigger and more complicated, and things like kind of grows exponentially, literally exponentially, right? And so let me just mark this. When we talk exponentially, there's an exponent involved. It's not just like really big. Okay. So to kind of finish this part, there are problems that get exponentially bad, but quantum computing has aspects to it that are exponentially good. So can we use the exponentially good part of quantum computing to control the bad part in some of the applications? So,
Amazing. Okay, so that answer opened up a bunch of topics I want to get into. I think in order to get to some of the quantum computing specific questions, I need to invite you to share. You referenced these weird ways that quantum mechanics operates.
mhm,
And so I know that you're a mathematician, and I do want to find out kind of the perspective difference you see as a mathematician versus physicist. But before we get there,
mhm.
if you could just reference some of the ways that quantum mechanics is maybe not, well, we can call it weird or spooky, as Einstein
Yeah.
said,
Yeah.
but the ways that it sort of defies our expectations from classical physics.
Okay. So let me throw one thing out there, just to give an idea of what you can't do with so-called quantum data. So data that's been encoded for use in a quantum computer, or it may come out of a sensor and an atomic clock and things like this. You can't copy data. So this notion of, hey, I got a database of, I'm going to put all my quantum information in my database and then use it later. The moment you try to use it, it destroys the copy that is in the database. So there's no copying of information. They said, what do you mean I can't copy? And anybody who's coded, you copy data all the time. You do these sorts of things. And, so what does this kind of remind us of? Well, if you go back to Star Trek and teleportation, right? Yeah, remember? I mean, they're standing there and then you get the kind of, shimmering and they show up someplace else. And you don't have 2 copies of them, you have 1. And in fact, once you start getting around quantum methods, getting into them, there is this thing called teleportation, and that is related to it. So so I'm stating this just as a before I sort of tell you about, superposition and entanglement, right? Um, this looks like a major roadblock, and I'll touch on some other things. Okay, so the first thing is this superposition notion. And this is the thing where people, and truthfully, I really don't like this expression, it's 0 and 1 at the same time. And I don't like it because it's just meaningless if you say it that way. It has a very specific technical meaning. And if you know what that is, you can shorthand and say that. But if you don't know what it is, I have no idea what 0 and 1 at the same time is. It's not like 0.5. Um, it's the idea that in classical computing, and here I mentioned zeros and ones, but we can enlarge this to thinking about numbers and text and videos and sound, all the data we represent. Um, it's there. It's somewhere. So, for example, this recording, as we discussed, will be part of it will be on my computer. It will be upgraded to another computer, right? Copying it. No. And things like this. But all that information has a physical place it lives, right? So if you were to open up your phone somewhere, you'd find these little memory modules. And if you took out a microscope and you could rip it apart, you'd find, oh, that's where that zero is stored and that's where that one is stored. Okay, quantum computing doesn't work that way. And in fact, it doesn't even deal strictly with zeros and ones. We deal with quantum states and we deal with probability, right? Um, so the idea is that, well, yeah, I mean, we can include zeros and ones, but once we get going, we can put this quantum information into a state where, first of all, you're not allowed to look at it. If you look at it, it destroys it. So there's another gotcha. Yeah, you look at the data and say, bye-bye, it's all. And in fact, what happens is it becomes zeros and ones, but probably useless at the time unless you're doing it in a controlled way. So what we deal with instead are these notions of the probability of something that's holding quantum information, uh, ultimately giving you a zero or a one. And now if we enlarge, right, we start thinking of numbers and text. So every byte, if you think you're typing something, something simple, you look down at your keyboard and you type a capital H. Okay, well, that takes 8 bits, 8 zeros or ones right there. Okay. Um, that's fixed, right? And so ultimately, quantum computers are only useful if we can get to those zeros and ones. So that does happen, but in the middle, all the information has probabilities associated with it, and particularly as you start adding more and more and more. So the trick is, without looking, to try to affect the qubits that's holding this information in such a way that while we can consider things very broadly, it's almost like a funnel where we're narrowing the possibilities probabilistically, right? We're saying this has the highest probability of being the correct answer. And so this is another thing. Many quantum computing computations are not exact. It's not like, here's the answer. It's like, congratulations, that you have a 98% chance of that being the right answer. So what do? You run it again. And if you get the same answer, right, then you run it again and you get the same answer. And so this other part that's beyond the simple zeros and ones, you start dealing with probability. Gee, I skipped that part, right? I go back and look at that. Also, the numbers are more sophisticated. We deal commonly with things like integers, 1, 2, -12, whatever, what we call the real numbers, the decimals, the fractions, and things like this. They're not sufficient. You need a larger class of numbers, and we throw in the square root of -1 to get complex numbers. Because in fact, as much as this may seem exotic, oh, the square root of -1, what is that thing? Right? The universe runs on it. Weird as it may seem to us, right? So the math gets a little bit more complicated, but you can explain it all mathematically. So the way I described it was the algorithms, you start with a number of qubits. You do things to them. There's this funneling process. You get down to what you hope is the correct answer, or at least probabilistically. There's something else that happens, though. I mentioned that you can't copy quantum information. Well, there's something called quantum entanglement, and this is the spooky action at a distance that Einstein and let me say, he said it in German, right? And all these things get paraphrased and this and that and whatever. But the idea is that two of these quantum particles, qubits, and I'm just going to stick to qubit. A qubit is a quantum bit. It's the thing that holds the information. It's possible to combine two qubits in a way, usually temporarily, so you can no longer distinguish them, that they operate um, not it's a weird way of phrasing, not independently of one or the other. So that is, if I look at one and I know how it was prepared, I can tell what the other one was. Usually things are completely independent. I make that a zero. Well, it doesn't mean that thing over there is anything else, right? And things like this. So entanglement brings them together. And this, in many applications, isn't a direct substitute for copying, but it's an extra thing in our toolkit that does not exist classically. So quantum programming, quantum coding is very different. And you can be the best classical programmer in the universe. And that doesn't mean you're an amazing quantum coder. You have to learn this. And so many companies like IBM, like Microsoft, the big companies, I've written a book to try to explain this type of coding. And Jay Gambetta, who's the head of the IBM program, quantum program, said years ago of people, sometimes you're thinking too classically, right? You literally have to change the way you think about this. And the best ones to do this are the 12-year-olds and the 14-year-olds. I have met so many smart students who are in their teens who don't have the baggage of decades of thinking classically, right? And they take to it and like, yeah, okay, we'll do it that way. That's fine. Now, eventually, all this will get abstracted away, and you won't be down on the bare bones. But this is the point, that it's really completely different, and how to do it. So there is a learning curve. Um, I remember when I was learning it, I'd be so proud of myself. I understand this. This is great. And I'd go to bed and wake up the next morning and say, I don't understand this at all. So it's for a while, it's 2 steps forward, 1 step back. So for the people who are listening, don't expect just to go linearly. Oh, I know this, and now I know this. I know there's going to be some confusion as you kind of relax and get more comfortable with the concepts, and that's completely normal.
Mm. Well, that gets at this idea that you reference in Dancing with Qubits around quantum computing being very good at very particular things. In terms of what we know now, of course, you leave open the possibility that there's all kinds of things we don't know yet. But you reference specifically extremely complex computations and hard problems.
Mhm.
So could you speak a little bit about, I guess I want to carry this line of like interrogating a misconception that quantum computing is just the quote next step of computing as we currently understand it. Like it's like a continuation of Moore's law. Yeah.
Um, sure. And by the way, because people do ask me, so the name of the book is Dancing with Qubits. It's been out in the second edition for about a year and a half, or as I say, the second and final edition. I can't spend my entire life working on it.
Famous last words.
Yeah, I know. I said that once before. But the dancing part is, we were just talking about entanglement, right? So qubits come together for a while and the algorithm proceeds and then they come apart. So for some reason, when I was giving a talk, I was just imagining this notion of people coming together, and then separating after a while. And so I called it, when I was speaking, the dance of the qubits. And later I thought of that. If we look classically, even at something which is, very simple, I give you a deck of cards and I scramble them and I want you to just sort them into, the normal orders with the types of cards they are and things like this. There are many algorithms to do this type of thing. And then the more structure you know about the problem. So the point being is that there's more than one way of doing something. And sometimes you would say, this problem is really just too small to apply this fancy thing. If I give you the numbers 2 and 1 and say, sort them in increasing order, you'll say 1 and 2. You don't have to haul out the big machinery to do these types of things, right? And this happens classically. You kind of look at the problem and you decide how you're going to approach it. The same thing is true with quantum. You don't use quantum computers for little problems. You don't use them for problems that classic computing does a perfectly fine job. So there's a threshold as we think of problems. How big does the problem need to be before we would consider when quantum computing would be more efficient? And this is a misconception because you hear so much about this quantum computer and that quantum computer. These quantum computers today are really way too small to show any significant advantage for most of the things we care about. right? And so, oh, it's imminent and things like that. Well, maybe not, because you personally are not dealing with a problem that is that big. And in the same nature, yes, technically you can compute anything with a quantum computer, but in the same way, you would never use a quantum computer to compute 1 plus 2, right? If that was the only thing you were doing, right? Maybe in the middle of something else, you might use it, but it's just today's classical processors are so optimized for some of these things. So you have to be intelligent about the types of choices. So large problems and only certain types of problems, we believe, will make sense. So these problems are some of the things we talked about related to chemistry, material science, maybe eventually new drugs and things like this. Batteries, right? And when we think about energy, as an example, there's a lot more to just thinking of electrical grids. There's like storage. There are issues like people are using solar panels. Can we use quantum computers to make better solar panels? Lithium, which is in a lot of batteries, is a very small atom, right? If you go back to your, take out your periodic table from a lemonade card you carry around with you, maybe. It's way up there. It's a very small thing. So lithium batteries are maybe going to be one of the first things that quantum computers. It's a relatively small problem, yet nevertheless, this whole chemistry thing is something that classical computers lose steam in trying to do. So you have to be intelligent about this. You don't just say, quantum computers, they're the amazing supercomputers of the future and they'll do everything. No, no, it's going to be in combination. Just like today, we use GPUs from NVIDIA, from AMD, from others and things like this for graphics. We're using them now, certain types of computation, AI. That's not hybrid. It's just modern computation uses a number of different processors, including like something going from my phone to the cloud and back. How many actual processors of what type were involved? So the future world of computing will continue to be heterogeneous. And we're just inserting quantum computers into the mix to help us solve the types of problems that it will be good at.
Amazing. Final bit on the maybe more elementary side, going back to the, supposedly spooky, whatever the word in German is, um, quantum mechanics. You have this really helpful metaphor at the beginning of Dancing with Qubits, um, about somebody going through a door with and flipping a light switch. And I think if you could share that here, I think it would help illuminate some of how this
No
is.
pun intended, right? I'm
Yeah.
with the lights. I'm illuminating the light switch. Okay.
Yeah, exactly, exactly.
Uh, well, thank you for reading the book. I mean, that's clear, or at least the first chapter.
I read the chapters I could understand. I'm unfortunately not a mathematician, so there were certain
No,
chapters that I glossed.
no, it's actually fine. And in fact, the way I structured the book, just as a quick aside, was there are a lot of people who earlier in their lives took math, right, in one way or another. Maybe they liked math. In fact, the publisher made me insert something like, "You need to like math." Um, but people might have taken math, sort of high school or in college or something like this, and maybe took an engineering class or something, and then life happens, right? You may not remember all this stuff. Or you may not have really known how it worked in the first place, but you could use it. So with quantum computing, because it's so strange the way we described it, people can be afraid of jumping into it. Like, oh, I've got to learn 3 years of physics to do this. Well, it turns out you don't, right? And that was the point of the book. And so my plan is, or it was with the book, to ease you into this, to explain things, almost like I'm standing right next to you. And as questions come to your mind, I want to be thinking of them before you do, right? And I want to give you a way of thinking about this. So some people say, well, the first third of the book is just math, elementary math. And it's like, yeah, and that's the part that people thank me for writing, because then they can understand the second two thirds, right? I'm not aiming it at physicists. I'm not aiming it at graduate students in physics. I'm aiming it for everybody else, right? And so that's a little bit like that. So, in fact, the first chapter is the warm up, is to talk about my so-called Q switch, I talk a little bit about AI. I invoke baseball, and a few things like this. And so the Q switch was my attempt to try to talk about this idea of not being able to look at quantum information. And Q switch, QU switch, I totally made up this word. It was just to evoke quantumness, right? And things like this. It took me longer to make the diagrams than to actually write the section. But uh, so here's the idea: is that you have a special a new type of light switch, all right? And here, it's toggle up, down, and things like this. Um, well, this new Q switch has extra power to it. It doesn't just have on and off. It has some extra characteristics. And the extra characteristics is, instead of just looking like a light switch on and off, and that's a great way of thinking about bits, 0 and 1, true or false, on off, things like this. It looks like a sphere, right? And yeah, it turns out mathematically we put off on the top and on the bottom. That's a remnant. But there are all these other sorts of stages, right? It's you can imagine a dimmer switch as being in between, but this is even more sophisticated. It's sitting on the surface of a sphere, of a ball, and the state can be anywhere you want in there, right? But you you can't look at it. The moment you look at the Q switch, it immediately flips to 0 or 1, right? But when you're not in the room, in theory, something could be controlling it and moving it to some of these other states, right? Um, and so the question is, when I look at it, when I observe it, and here, I can't like have a camera looking at it. That cheats too. Any way of looking at it. How does it decide to go to 0 or 1? My fancy switch here. And the book explains a little bit more about how you change these states and things like this. But here's the deal. So if you're already on or off, you stay on or off. Nothing changes. But as I described it, it's a sphere. So think of the Earth maybe, and think of the equator. Right? If I'm in the northern hemisphere, but not at the pole, then I say you have to choose whether you're on or off, right? Or we'll keep within the planet. We'll say the North Pole or the South Pole. If you're in the northern hemisphere, my instruction to you is you must go to the North Pole or the South Pole. That's the on or off. So we start in the northern hemisphere. Odds are, if you have to choose now, what is choosing? Nature's choosing. Really, it's not you. Odds are you're probably going to go to the North Pole, but not definitely, because you are a little bit south. Even though the probability is a little bit less, you could still say, "Oh, what the heck? I've already come this far south. I'm going to go all the way down to the bottom." And the same there. So if you're not exactly at a pole, you could potentially go to one, pole or the other, on or off. The interesting thing happens at the equator, because here the choice is equal. I have no preference. I'm on the equator. I could go to the North Pole. I could go to the South Pole. The light could go on or off. Right? And this now gets into quantum randomness. This is true randomness from nature. And in fact, it is 50-50. If you look at the odds, just like rolling dice or flipping coins is never exactly, if you flip a coin 100 times, you may get 50-50, but you usually don't. If you do it, 10 million times, it's going to be pretty close to that middle. So this is, as we were talking about the probabilities, the algorithms, when we're talking about one qubit, it's trying to move that little point, that little value, as close to the North Pole or as close to the South Pole as we can. We're trying to increase the odds if that's the right answer. That's what the algorithm kind of looks like. So thinking about it as a sphere is not a bad way for one piece of information. Now, in the future, we're going to have hundreds of thousands of these spheres all working together and being entangled and things like that. So this model goes out the window, because you just lose your brain if you try to think about all this sort of thing. But this is the weird idea, that probability, this notion of, nature is forcing you to choose. And what we do is we try to, you know, nudge it toward the right choice if we can. Now, one thing I do want to say about this randomness is it turns out it comes in very handy because when we talk about security and generation of keys and things like this, if I were to go into, let's say, Python or another programming language and say, give me a random number, it's not really quite random. It was generated in a certain way by several operations, but it started from some point and then did a bunch of stuff. And then you say, do another one, right? And in fact, I can give it what's called a seed, and it will generate the same sequence of random numbers over and over and over again. But with nature, it's always just random. So it has very positive, this quantum roundness has very positive aspects for cybersecurity and for several other things.
Well, this is a very natural segue to talking about the next part of chapter 1,
Okay.
which is quantum cryptography. And
Yeah.
so a lot of people are, pulling their hair out talking about, when quantum computing is sort of meaningfully implemented, there goes all of our privacy. Talk to me about what the real fear within that is, like what we need to be considering, but also why that's a little bit maybe overstating the case.
So I love this example because it forces people to learn more math. Really. Yeah, I'm a mathematician by training. Um, Even like with Pi Day, okay, I accept you learn a little bit more, but I think there should be a trigonometry quiz to celebrate Pi Day. If you're going to do it. The thing that people have to learn more about to understand this is factoring numbers. Now, some numbers are incredibly easy to factor. So 15 is 3 times 5. Okay, yeah, not a hard problem. Um, but what are 3 and 5? Well, it turns out these are prime numbers. We can't further factor them other than into themselves and 1, right? So this notion of prime numbers comes out. And it turns out that there's a really major part of theoretical mathematics called number theory, which is dedicated to prime numbers. These integers that we talk about, even if we just talk about the positive ones, 1, 2, 3, 4, 5, 6, 7, the structure is extraordinarily complicated, right? And the amount of math that people have put on this, right? So are there an infinite number of prime numbers? Well, yes, that's one of the first proofs you learn about how to do that. Can you keep generating them? Do they stay close together? Well, sometimes, not always. What about 3 and 5? Well, 5 is 2 plus 3. Are there other prime pairs like that? Turns out, yes. Are there an infinite number of them? Yes, there are. Prove it. Okay. Go and take 3 years of college math, and you can prove it. And things like this. So the point being is that, a lot of people in their earlier education might say, oh, okay, so 8. 8 is 2 times 2 times 2, right? There are some numbers, first of all, very, very large prime numbers that can be very difficult to determine if they are prime. And there are also some very large numbers that are the products of 2 primes. That's hard to break into those 2 pieces. This doesn't mean all large numbers. Because, for example, if I take 10 and multiply it by itself 1,000,000,000,000 times, that is a very large number and completely trivial to factor. It's a lot of 2s and 5s, right? In fact, it's 1,000,000,000,000 2s and 1,000,000,000,000 5s, and we've just done it. But other numbers could potentially take, via the best classical methods we know today, the most advanced number theoretical ways of factoring, could take millions of years. Okay, well, that's curious. Why do I care? Well, when you do cryptography, so here it is, you're taking information, you want to encode or encrypt it, give it to somebody else, and one way or another, they decrypt it. You don't want that to be easy to do, right? You need to do it. You either have to have the exact information to decrypt it or be able to solve some very, very hard problem. And it turns out that the hard problem is the factoring problem. All right, so let's go back 30 years. Peter Shor then a scientist at Bell Laboratories, now a professor at MIT, came up with a quantum algorithm, which was theoretical at the time, because there were no quantum computers, right, that could factor such numbers almost exponentially faster. And now let me give you an idea of what I mean. And I refer to this about when we say exponential, we mean exponents. Okay. So let's say something takes 1,000,000 seconds to do, 10 to the sixth seconds. That's a lot of seconds. I forget how much it is. I keep doing this calculation and then immediately forget it. It's a long time. Okay. Um, if I have what's called a quadratic improvement, that means we're taking the square root. Maybe we multiply by some funny number, but basically we're taking the square root. So instead of taking 1,000,000 seconds, we take the square root of 1,000,000. That's 1,000 seconds. So that's pretty good. It's not that perfect because, as you start looking at a billion, a trillion, quadrillion, things like this, that square root is still getting pretty big. But what if I told you instead of taking 1,000,000, which is 10 to the sixth power, I could do that in 6 seconds, that exponent, 6 seconds. So we go from 1,000,000 seconds to 6 seconds, 1,000,000 years to 6 years, right? That's pretty darn good. And that's the holy grail of computation. And that's what Peter Shor showed, that there is an algorithm that could factor large numbers almost exponentially. And there's a little fuzziness in the numbers. And once quantum computers started to come along, albeit we're still too small to do any of this, and people started saying, wait a minute, things like Bitcoin rely on elliptic curve cryptography, which lo and behold, under the covers, could be broken by this factoring. A lot of protocols like RSA that are in use today could be broken in theory by this. And people look around and say, wait a minute, if you get powerful enough quantum computer, you could potentially break the cryptography, and not just like if you're sending credit cards around, encrypted databases and things like this. They could get access to financial information, medical information, national security secrets, and things like this. And some of these things you might say, well, look, okay, 30 years, if they know that I spent money on this credit card I don't even have anymore, I'm probably not too upset. But national security secrets are decades, right? And things like this. So this is the potential threat. So this is not something anyone has to worry about today, like your credit card on the web or things like this. But what so-called bad guys are doing is this process called harvest now, decrypt later. So get as much of this encrypted, confidential data as you can from whatever sources and just store it someplace. And then, if quantum computers get powerful enough, then crack it and then see what you can do with it. People like to call this Q day. I actually don't like this phrase. The day that you wake up and quantum computers are powerful enough and everything you know about is broken. Uh, and part of the reason why I don't like it is because no one's going to announce this Q day. Yeah. People talk about Y2Q instead of Y2K, right? And the actual Y2K came in with a whimper on a specific date, January 1st, 2000, but people had done so much prep that really nothing much was broken. In fact, I think what's going to happen, and this is even scarier, is you're not going to find out today is Q day. You're going to find out Q day was 3 years ago. Because bad guys aren't going to necessarily be saying, hey, I just broke all your encryptus. They're going to be breaking it and doing stuff with it, right? Yeah. So what do you do? Okay, well, there are different ways of encrypting your data. If it's potentially susceptible, eventually, and not all schemes are, but if it is, move to a more modern scheme. And the U.S. National Institute of Standards a year ago, August, came up with 3 different encryption standards for slightly different uses. They've since come up with one more. They will continue this process. So the idea is move from the older ways of encrypting your data to one of these new standards. And you should, at least for a while, be safe. There's no proof, no serious mathematical proof that says this cannot be broken, ever. There's just kind of a probabilistic view. It's understanding what sorts of computations quantum computers can and can't do. Um, and so what has to happen is you don't just switch, you move into more of the zone of what we call crypto agility, right? You don't just have a hodgepodge. Oh, I have RSA over there. I use elliptic curves over here. Oh, I just acquired another company. They do all this other stuff. And by the way, I've got these 3 clients that are talking and looking at my databases and things like this. You have to inventory what you've got, right? And then you have to have a plan to move to these new types of those standards. But the process then has to be that you can easily swap in something new, right? It can't be such the spaghetti, right, implementation of cryptography. And this is what crypto agility is. It's modular, right? It's well thought out. You have a good working inventory. You can make the conversions much faster. So even though we believe that nobody has a quantum computer that can do this, and the big question is when, right? Security companies is like, it's sooner than you think. And quantum computer inventors say, if I were being honest, it's later than you think. But it's somewhere in the middle. But the whole process of converting to this, in some cases, can take up to a decade. So start yesterday. We don't know how else to tell people honestly that they have to get going on this, right? And moreover, they're better than what we got. Quantum or no quantum, they're better than what we got. Crypto agility is much better for cybersecurity. So be smart. Do this. I mean, what more do you want us to say? Right.
Yeah, well, even thinking about, I used a few years ago, I was using LastPass. And I don't know if you saw this, but there was a big LastPass breach where it's sort of this exact scenario you're describing.
Uh-huh.
The attackers got all of the encrypted passwords. And now there's kind of this like looming prospect. I mean, the big kind of messaging there was change all of your passwords. Because now any passwords that were in your vault are now potentially at some ambiguous point in the future going to be either public information or in the hands of bad actors. And inevitably all these other, I shouldn't say all these other, but lots of these other leaks are creating the same vulnerabilities
Uh-huh.
that when we get to that point, it's a big problem. Whereas it's not a problem at all right now, but as you said, you might not realize it's a problem until 3 years later.
That's right. And I glossed over several of the details. There's asymmetric, symmetric encryption. Um, the factoring is really related to the keys that you use. Well, if you and I, if I want to give you information, I have to give you a key. How do I do that securely? Because if classical means can somehow break in and give you the key, it doesn't make any difference with quantum or non-quantum. You have the key, right? If you shouldn't have it like this. So now people can we encrypt the keys? Can we use these quantum standards to encrypt the keys? Can we use something called quantum key distribution, which at least tells me if I am sending you a key, I can tell if anyone else looked at it on the way. And then you just say, well, we're not using this, right? So at least you have that sense of security that you're getting something that hasn't been observed. And in fact, it goes right back to that, right? Remember, if you look at it, it becomes useless. So you can tell if someone has looked at it.
Mm. Yeah, it really is. It bends the brain thinking about this stuff relative to how we thought about computing. One question, kind of switching hats for a moment. You worked at IBM for decades, so you're very familiar with how large corporations approach these initiatives, like thinking about developing crypto agility. From that perspective, and also in the consulting and advisory you do, what would you say are the like top pieces of advice to developing crypto agility? Because of course there's a lot of institutional resistance to change just about anything, as more and more as the corporation gets bigger and bigger and has more success.
Um, so one basic question is, it's nice for me to talk about these new quantum standards and crypto agility. I personally, as a consumer, am not implementing them. Honestly, I mean, I'm not writing code to do all this. I rely on others to do this. So I rely on the vendors. Apple, interestingly, was one of the first ones. So if you use iMessage, that's actually quantum protected. They were one of the first to adopt these. So say anything you want. I don't, I don't know. Um, Look for the vendors. So early on, the people who were developing the quantum computers often had uh, within their security divisions an effort to get people to move to a so-called quantum safe future. And I consider that a pretty ethical move. Like, yeah, okay, we're developing the technology which could eventually cause a major problem, but over here, we're telling you how you can avoid the problem, right? And so it started a lot of the big consultancies. There are a lot of startups that do this. But to me, it's even more interesting. You see some of the smaller vendors do this. Um, and by the way, when I say small, I compare to, at one point, IBM had almost 400,000 people when I was there. And yeah, so if you have like 12,000, I don't insult you by saying you're small. It's just you're smaller than them. Um, you're starting to see the vendors that IT people know and work with all the time that consumers may not hear about. I mean, as a consumer, you hear about NVIDIA. You know who IBM and Microsoft are. But there are hundreds of other vendors that do the guts of the IT, the actual infrastructure and hardware and software. That's what's interesting to me. More and more, there are announcements of they're doing it for their products, for data security, for moving information in and around. So, become generally familiar with this notion of crypto agility is, and there's a sequence of steps. I wrote a paper with a colleague for NetApp several months ago when I was with Futurum Group, and it's still out there. You can look for it, NetApp, Sutor, Quantum, whatever, you'll find it. And it lays out, so you have to inventory, you have to have a plan, you have to prioritize, you do things like this, eventually. Now, also, the European Union, as an example, has a very good document for its member states that says, this is what you need to do. This is what we expect to do. What will happen, and in some corners is happening already, are saying, I won't work with you, or I won't work with you anymore unless you have implemented these so-called post-quantum cryptographic standards. So it's becoming a requirement in government, and it will probably more and more become requirements in what we just say corporate contracts and things like this. So talk to you if you're big enough, you have your own security team. Talk to them; they must be on top of this. If somebody tells you it's not a threat yet, you can ignore it. Consider getting somebody else who knows actually what's going on, to be very blunt, right? Um, Work with your existing partners of who you've got and just completely educate yourself. I've talked to a number of these security people, and by the way, they are good. They are knowing what this is. Um, if you have a hodgepodge of security protocols and things like this, yeah, this is going to take time, and I'm sorry, it's going to be expensive. But so is losing all your data and all your client data and, invasion of your financial accounts and things like this. It's a necessary expense and it will lead to your being in a position which is much stronger than you are now.
Mm, love that. Okay, jumping back to your mathematician hat.
Okay.
Another topic you break down in the book that I find very helpful for folks who are looking to understand quantum computing is the idea of dimensions. And so you've talked about qubits, and you kind of run this comparison between traditional bits and bytes and qubits, and then you get into this topic of dimensions. So I want to invite you to sense make that for audiences.
Well, so people I think know what two-dimensional is, right? Um, Flat, it's a piece of paper, right? And you can draw things. You might think of the surface of your screen as two-dimensional, right? And things like this. And people who don't get into this in the math, maybe they remember something called a Cartesian plane. Remember that? Where you got the x-axis going here and the y-axis. And then someone gives you a number like 3, 2, and you bounce over 3 on the x and you go 2 on the y and you draw a little circle. Okay, so that's two dimensions. Well, there's nothing for me to say instead of just giving you two numbers, 3 and 2. I could give you 3, comma 2, comma 1, comma 6, comma -5, comma, I could give you 1,000 of these numbers. And this stuff of the coordinates and the geometry and the algebra carries through, right? And also when you get above 2 dimensions, you get other tools that enter into this as well. So mathematically, 2 dimensions, 3 dimensions, you might have heard time is the 4th dimension and all this sort of stuff. For the moment, forget all about that. It looks very consistent mathematically. You just have a lot of numbers that say in some space, move over this far, move up here, go over there, whatever. And even if you can't visualize 4 dimensions, 5, which like we don't typically, to do this, the math looks consistent. It's a list of numbers, right? And you do things with them. And you can compute whether 2 things are perpendicular to each other in these amazing multidimensional spaces. All right. It's kind of fun too. It's just relax. Don't say, what does it mean in the real world? Well, it means a lot because as we talk about quantum, and as I said earlier, quantum mechanics is the way nature works, and maybe it's a computing model for the apps, which are you and us. Congratulations, you're dealing with an infinite dimensional space. So none of this 2 or 3 or 4 or 6 or 7, it's infinite dimensional. That blows your mind. So you want to talk about real world? You're real world. So you can exist without infinite dimensional spaces somehow controlling what you're doing. All right, quantum computing makes this a little bit easier. So when we start, and here, just to keep the numbers simple, I mentioned we use these complex numbers. 1 qubit, which is, as I said, kind of a combination of zeros and ones. We have these complex numbers. We throw in square root of -1, is 2-dimensional. And so you basically have 2 numbers that are associated with this. Now, compare that to a bit, which is simply 0 or 1. None of this that's in fact 0-dimensional. That's just 2 points. That's 0-dimensional. All right. So 1 qubit, 1 piece of quantum information, 2-dimensional. And there are infinite number of possible values, not just 0 or 1, infinite number. We control them, what they are. They're not arbitrary, but they're still an infinite number. I add another qubit. That goes to 4 dimensions. And you say, I can do math. I can say that 2 plus 2 is 4. It turns out, yeah, that's true, but it's really 2 times 2, the way the math works. Because when I add a 3rd qubit, it exists in an 8-dimensional space. 2 times 2 times 2. And I add another qubit, it's a 16-dimensional space. I have 10 qubits, it's 2 to the 10th power, or 1024. So you have to represent this in one standard ways of doing this by 1024 numbers. It quickly gets big of how to do this, but this is the good exponential growth. It's 2 to some power, to some exponent. And that's how things get. So you better become awfully comfortable with this slightly abstract way of dealing with multidimensional spaces. But it is this power that gives quantum computing the potential of dealing with very large problems. One number we like to toss around is when you get to 275, what I'll just call perfect qubits that operate the way they do in books, as opposed to the noisy physical qubits that we actually build in the computers. When you have 275 of those, the amount of information you can represent is more stars than there are in the observable universe. Okay. In fact, I may need to correct myself. I think it's more atoms, than are in the observable. And I think that's correct. In the observable universe. In any case, it's a really big number. So these quantum computers with 275, let me just say, very good qubits are on the horizon. It might take a while. It might take 10 years, but they are on the horizon. So you think, how could you possibly squeeze something which is like all the atoms in the observable universe into a single quantum computer? And it goes back to what I was saying. If you looked in your iPhone and you broke it up and you got a microscope and you looked in the memory and say, there's the 0 or 1. Quantum doesn't store information that way, right? And that's the power that you can set up these problems that potentially have so much information, and your algorithm better funnel this down pretty fast, right? It doesn't consider every single possible answer at once. That's a misconception that people say. right? It looks from it. It's rather, it can set up the problem so that you can quickly funnel it down to a smaller number of likely good answers. Um, but that's pretty mind blowing. I know I'm using this kind of 60s terminology, but
No, it is.
kind of is,
100%.
right? And that's the power. And it's also why, look, we don't solve little simple problems, right? We don't do baby AI problems. Or if AI works great with classical, do it. Keep doing it. We need to save this. And that's the gap between where we are now and when we will get to what several of us call practical quantum advantage. It's not the cute problems. It's not the demo problems. It's not the exotic things in the back of a lab that 10 people know what you're talking about. It's, eventually, now let me jump forward 20 years from now, if you have a retirement account and you say, I'd like to rebalance this, for these reasons, I will tell you a quantum computer will almost certainly be in the background helping you then. Because if you think of all the connections between the stocks and the bonds, and they're not independent, right? If a hurricane is going to hit the southeast of the US, for some reason, Lowe's and Home Depot, right, their stock can be affected because of all that plywood, right? And things like this, and everything is interconnected. And this is what I was saying. Small problems, a relatively controllable amount of data when you start considering all the combinations. So for doing this type of optimization, you may very well see. So just as I said, you may not wake up and find it's a Q day. You may not wake up and find out that you're using a quantum computer, 15, 20 years from now. And just in the same way, I used to ask people, have you used Linux today? I say, oh, no, I'm a Mac person. I'm a Windows person. I don't use Linux. Oh, so you haven't used Google, right? You haven't used the internet in any way. So this is the type of thing is that eventually it's just going to slide itself in there, right? And it will be used in some places.
Got it. Well, you brought up the acronym du jour. You referenced AI. And so I want to spend some time sense making through that because, of course, there's really exciting things happening at sort of fringes of quantum machine learning, but there's also a lot of misrepresentations about the relationship between quantum
Right.
computing and AI.
So when I give talks about this, I sometimes joke of saying, well, if you're looking for funding, quantum's a nice term, but if you throw in AI and then you do it on the cloud, and what the heck, throw in blockchain, you're guaranteed, right? And sometimes some of these announcements look like this, right? And they're highly questionable. There's certainly great academic work and some advanced research work on this, but there are some fundamental limitations to this. So the first thing is what we call the data problem. So if you think of ChatGPT, some of the other types of systems, Claude and things like this, they have scoured the internet, sucking up almost every bit of text that they can possibly find, not to mention video and things like this. This is all classical information, right? It is very, very expensive and time consuming to take classical information and put it in a quantum form. In fact, in some cases, it can be exponentially hard to do this because of all these qubits and, some superposition and things like this. So if the problem is really, really difficult to do in the first place, you have to think, is it valuable, right? If I'm wasting, if I'm wasting like a year to load up this information in a quantum computer, which doesn't exist, right? I better have something useful to do, or maybe I should just get smarter about classical approaches to this. So a lot of what you see today are people experimenting with quantum for AI, and the results, though they don't, it's like, it's sort of kind of close to it, not too bad for little problems. It's like, well, that's a resounding success, you know? Now, you don't want to stop them because research takes years and you have to work with what you've got. You have to follow certain directions until they don't pay off. And you generally get smarter and then you have aha moments. So no one should stop that. But it's very risky to claim that your little quantum computer is the perfect match for machine learning or generative AI or things like this, because the machine is too small. You can't use a lot of classical information, things like this. So, um, even though some of these QML, quantum machine learning people, whatever, will deny this, and they probably don't like it when I say it, of all the sorts of applications that will really be seen as useful, with quantum computers, I think AI and machine learning are going to be toward the tail end. We'll be doing interesting things with chemistry for years before we do something that's so astoundingly amazing. Um, Now, the other race is, earlier I said there's going to be this threshold where the problem has to be big enough to make quantum even worthwhile. Well, supercomputers for most of our lifetimes have been fairly rare. And now they're like all over the place. Every one of these massive AI data centers with all these GPUs and things like that. Think of the computational power in those things. So it's not that hard to find massive computational facilities, which means you can probably do it classically if you wanted to, which means you're not going to need quantum till later on, right? So you see this, that the bar is moving to when quantum will be absolutely required, and it's specifically in the AI area. So look for good research, but outlandish claims of advantage and this and that are probably tiny, tiny problems. And we could have done it just fine classically right now. But eventually there's hope.
Mm. Well, this gets to something you gave a talk, I believe, at Quantum World Congress in 2023, where you're referencing the elephants in the room. Um, and what I'd love to spend a moment talking about is a kind of state of the quantum computing 2025 kind of moment that we're in.
Okay.
So, are those elephants in the room still elephants in the room? Are they maybe smaller elephants? But then also, you've referenced quantum chemistry a few times. So, if you could share more about what you're actually seeing coming out of quantum chemistry research that's exciting you, and or anything else that maybe isn't quantum chemistry that is really exciting to you.
Okay. No, you are testing me about going back to a talk I did 2 years
I
ago.
know it's unfair of
But
me. I know.
but thank you. You did warm me up with the data problem. And that is, so the so-called elephant is the thing that people would rather not talk about. Um, what in the range of things that people can talk about, they could say perfectly truthful things, right? Um, and when you get beyond that, and you can't say everything because it's confidential and things, but you could say perfectly factual things. Now, when you start getting into over marketing or hyping things like this, all right, I'm going to give you a little bit of room to say what an amazing company you are. I posted something last week where at Quantum World Congress, IonQ and Quantum and Quantinuum were right across the aisle from each other, and each of them said, the leader in quantum computing, right? And I could give you 12 others. There's one very, very funny example that it's like they must have been smiling when they said this because no one in their right mind would ever believe this, right? Okay, so you're starting to get into that. Then sometimes people say there are two types of lies. There's lie by commission. I am actively lying to you, actively telling you the wrong thing. And unfortunately, there have been examples of that where people just went so far overboard. But the one that's a little trickier is lies by omission. I'm just not going to tell you everything you need to know to really make the proper conclusion. I'm going to lead you in that way, but if you knew everything I knew, maybe you wouldn't conclude that, right? So, that's kind of related to these things. And so when you're reading, we talked about the data problems. I've seen articles that say, we generate petabytes of data every day, and thank goodness we have quantum computers to handle all this data. Stop reading. They don't know what they're talking about, or they're not being honest about it. It's just not true, and it's not going to happen maybe forever. Other than that, right, and things like this. All right, so here's some numbers. Um, of the people who make the core devices with the qubits, the hardware qubits, there are 85 companies in the world that do this, and these include uh, companies you've probably heard of, IBM, Google, IonQ, Quantinuum, Inflection. Yeah, I could go on till I hit 85, right? And things like this. Xanadu, Photonics, Quandela in France, and all these sorts of things. That's a lot of companies. That's an awful lot of companies. We don't have anywhere close to the number producing classical processors at this point. I mean, the system. And in fact, in the 1970s, when we were in the mainframe era, it quickly went down from about 7 to 2 or 3. And IBM is one of the ones that have survived. Right? So the state is that there's a lot of companies doing this. Recently, there's been a lot of money flowing into this. There have been several uh, $100 million plus deals lately. There have been some deals of companies who have announced that they're going public, usually via SPACs. So it's a healthy market, but it's heading toward a point where it will not sustain 85 companies. Now, my number was 86, but IonQ bought Oxford Ionics. So they absorbed that, right? We will see more of that in 2006, right? We will see companies coming together, merging in different ways. It could be larger companies picking up technology. Sometimes they're just picking up people, honestly. When you get under the covers, these are not 400 people companies. They're like 3 guys, right? And a dog, if you're lucky, right? And things like this. So I think in 2006, you will.
You mean 2026?
That is probably true. Yes. 2026. And you can leave that in because I make these. Thank you. 2026 next year, because it's 2025 now. You're going to see a shrinkage of the current companies. You'll still see some more coming out because they're very smart people, usually in academics, who will do that. There are a few stealth ones I know about. Because the world just can't support it, and you can't keep finding investors to throw money at that. Also because if you look at, there are 10, as I mentioned before, there are about 10 different ways of doing quantum computing. 4 of them are the major ways. There's another one that's coming on strong. Silicon spin is coming on strong. There are a few exotic ones. A bunch of those are public or are about to go public in SPACs. So if you look at this and saying, oh, I do quantum computing this way, the world will only support 2 or 3 of those at most. Now, what does that mean if you haven't gone public yet? Well, I'm sorry, you just have no way to exit other than being absorbed or going out of business, right? In some way. So things will start changing that way. The money will start focusing a little bit less on raises, on venture capital or other raises, and more on acquisitions and SPACs and things like that. And that's healthy. I mean, and it's normal. Dude, that's the other thing. People are like, oh, quantum, I'm heartbroken. Quantum is so special. Yeah, well, you're still a startup, and your odds of succeeding are between 10 and 25%, right? You're still a startup for the same reasons. So things will start to change that way. Now, the one wrinkle, which I think is really interesting in the quantum industry, is the sovereign efforts. And so this is, a country or a region, such as the EU, let's say, says, we are not going to be reliant on other people to give us a future powerful enough quantum computer, right? For geopolitical reasons, historic reasons. The U.S. tends to dominate the computer industry over time. It just does. And you go to parts of it, certainly chips in Taiwan and things like this. So again, that was a general statement. But there are a lot of countries that are saying, look, this quantum, it's a new thing. It's a new chance to do this. It's a future of computing. We'll be damned if we're just going to follow that old playbook. So there are countries that are saying we will have homegrown, powerful enough quantum computers to serve us. We will have, if you will, quantum freedom of action. It's not just the computers, it's the supply chain, it's the workforce who's going to do this, right? If the number of companies does contract, that may throw an awful lot of physicists available, and they will find jobs elsewhere. So what you're going to see in 2026, to be clear, is kind of a mix-up of people and companies and money and how the money is being spent and things like this, all part of the normal progression of what we're going to see. And honestly, it would make it a whole lot simpler. Tracking 85 companies is a little tiring to do this, right? Um, should anyone want this information, I can tell them how to get it. But so the state is, there's great research going on, a lot of smart people doing this, but we have to not so much. There's not going to be one winner. There's not going to be even be one winning modality. The so-called, whether it's superconducting like IBM or photonics like Xanadu and Psi quantum, or neutral atoms like inflect. We can go on. Probably be two or three, and maybe in 50 years it's none of the above, because we'll be that much smarter. Right? We'll figure out new materials, new ways of doing the essential quantum stuff. So it will continue to be an extremely dynamic part of the industry, really, for as long as we're doing computing from now on. Right. So this is why so many of us are so passionate about it. It's like, we're here at the beginning. Intellectually, we talked about math. For me, it's fascinating stuff. And it's weird stuff. We talked about, the spookiness, the no cloning, no copying and stuff like this. It just has a really inherent fascination that pulls people to it. And whether it's, like the shows like the Quantum Leap, right? Or Quantumania, Ant-Man, Quantumania. It's one of these things where people hear you're doing quantum and they say, tell me more, as opposed to, thank you very much. I'm sure you find that interesting. Keep it to yourself. So it will keep the public's fascination for a long time, but I think 2026 will be an important sorting out year.
Got it. There were some other topics I wanted to get into, but you've already been so gracious with your time. So I'm going to limit myself to two quick lightning round responses, just so folks are familiar with the premise. So if you could just briefly describe quantum sensing and quantum networking, I feel like that would be a nice way to round off the conversation.
Okay. So quantum sensing, a very broad term. It could mean things like quantum atomic clocks, incredibly accurate clocks to many, many decimal positions. That has applications in what we call quantum inertial sensing, which is a very fancy way of saying, okay, well, if I move, let's say I'm up in the air or under the water, I'm moving in 3 dimensions. I'm going back and forth, left and right, up and down. All right. If I know very, very precisely how fast I'm going, and I know very, very precisely the amount of time that has elapsed, I can compute where I am. So imagine a totally dark submarine, right? How does it determine where it's going to go? This is important because GPS is being denied in more and more war zones and other areas around the world. Several years ago, somebody knocked out around Denver airport, 50 miles, GPS, right? So for this reason, and by the way, for completeness, you also have to figure out rotations, because, this yaw and stuff like this. So it's very complicated. It's all inertial sensors. We measure gravity in many different ways. We can find new things under the ground, potentially. We can find buried bunkers under the ground. So for a lot of this stuff, the military and defense is going to be the first market for what you're doing that. And then the final one I'll just mention of this family is quantum RF receivers, radio antenna. This is what it comes to. And at some point I saw a picture of a battleship, and you expect to see cannons and all this sort of stuff. And you look at it and you say, what are all those antennas doing on this? You've got satellite dishes and the things that look like cell phone antennas. We can do this far, far more precisely with quantum. They're far smaller. If you take a phone, let's say a big size iPhone or Android system, maybe make it 4 times as thick. You can have 6 bands coming in there, very precise and very narrow. So a lot of the future of communications in that regard will be, we think, quantum. Quantum networking covers a big span of things. One of it is saying, well, can I sometime quantum communications send you information that is secure using quantum means? What I and a lot of others who look at the technology think of is saying, well, no one's going to build one monolithic quantum computer, right? And again, I'm being a little careless with the way I phrase this, but the next statement is we will build big quantum computers from little quantum computers, right? That's the future. That means you have to connect them. And we don't just run a wire between them. We have to connect them in a quantum way that preserves this quantum information moving around and being able to do things where some of the information is in one system and some is in another, right? So you have to have a special type of networking called quantum networking that preserves this. And so it's going to be very, very important in the short term in data centers. And there's something called the Quantum Data Center Alliance, which is picking up, which is looking at these problems. So so it'll affect, as we talked about, it'll affect computation, it'll affect timekeeping, it'll affect GPS replacements, where are you going? Some of the fundamental networking requirements as we build out quantum and classical data centers. And then, as we talked about, some of the security things in different ways.
Yeah. I mean, there's an endless amount more that we could be talking about, but folks should just find you and work with you to get that information. I have 3 questions that I like to close every episode with. So the first of those is, what is one thing you wish people paid more attention to?
Personally, I wish they would use the opportunity with this new quantum stuff to learn a little bit more of what's behind it in terms of the science. Use this as an opportunity to go back and, we were talking about like the first chapter of my book or other books or things like this. Really take some time and go over and learn about the background, because as much as the high level sounds fascinating, the underlying level is pretty fascinating too. So use this as an excuse to learn a little more math.
Foundations are important, as is history.
Yeah.
What is one resource you recommend for making better sense of reality?
I would say the quantum reality. Okay. Uh, in terms of
I mean,
rather,
you
rather
can
than
answer this however
reality
you
in
want.
total,
Yeah.
right? So I will say most of the, so for quantum computing, most of the vendors have very, very good tutorial information about this. Um, if you are in the US, there are resources like the Quantum Economic Development Consortium, QEDC. They're very good. They do very solid reports. They're multi-vendor as well. So look for things like that are multi-vendor, but not necessarily multi-vendor marketing organizations, right? We're here to tell you how it really works, and the QEDC is very broad in terms of having reports and covering everything.
Great. And finally, what is one moment when your sense of reality was disrupted?
Uh, when we talked before about the no cloning
Mm,
information, that is, you can't copy quantum information because it's one of the most fundamental, constant things you do, right? Yeah, I'm going to store information over there. I'm going to use it later. I'm going to sort it later and think, no, none of this works. And so it's really shook me up in the sense of saying, I've got to get used to what this is. And if I can't do that, what can I do? And it's not a direct replacement. I have to think about getting a completely different toolbox and know how to use those tools. And I like that. I thought it was cool. I hope other people do too.
well, I do as well. And your amazing insights today will
Mm,
lead people that direction. So first of all, thank you so much for being on Urgent Futures.
absolutely.
Where can folks find you? How do people work with you? All of that stuff.
So I am LinkedIn, Robert Sutor. You can find me. That's the easiest way. Um, I do a number of things. If we want to talk about advisory or consulting and things like this, we can talk about that. One thing I'm trying to point people to is I have a Substack. I think it's Dr. Robert Sutor, substack.com. You'll find it once you find me if you go to sutor.com. But this is what I want people to know, and it's totally free. Um, I need to know what's happening in the quantum industry just for my job. And I had Google alerts and I had this, and then something would be announced and said, how could I possibly miss this? Right? So I started building this little news aggregator, collecting things here, there, and wherever. And I'm over, I think the number today was like over 440 different sources. And I pull in RSS feeds and I scrape, this is what I should have been doing other stuff, but this is what I did for my summer vacation. Anyway, we publish daily links um, of the news that comes out, and it's categorized about what it is. If you go to the Substack, Dr. Bob Sutor, or Substack.com or something, easy to find. You can subscribe. You will get a daily digest of everything that has, when we do it, everything that's been announced so far today and then yesterday as well. So it overlaps a little bit. And it will give you at a glance a way of just jumping to whatever part of the industry that you're interested in. And as I said, I did it for myself and I made it public. And I kind of feel like, well, as long as I'm giving it away for free, I want a lot of people to use it. So
Yeah, yeah.
that's why I'm hyping it a little bit.
Yeah. Well, reality studies is the sort of parent of Urgent Futures, and so it runs through Substack. So I'll be sure to link you as a co-author and point people that way.
Very good. Thank you.
But yeah, thank you again so much for being on Urgent Futures.
Great to talk to you.
This podcast is edited and produced by Adam Labrie and me, Jesse Damiani. The podcast is presented by Reality Studies. You can learn more by visiting realitystudies.co. And if you appreciate the work I'm doing, please subscribe and share it with someone you think would enjoy it.